outbreaks. So I'm pleased to welcome Matt Junge to today's CAM Colloquium speaker. Matt is currently at Baruch College in New York City after a very recent move after spending a year at Bard College. Prior to that, he was at Duke as a postdoc, where he worked with Rick Durrett, known to many in CAM. And prior to that, he did his PhD at University of Washington. The topic is fairly timely. So Matt has been doing a bunch of work on COVID modeling at college campuses, much of it with Lily Wang, who was a CAM PhD student. And when I contacted him about potentially giving a talk, he said, should I give it on particle systems or on COVID? And I thought that COVID was likely to be of general interest at this point in the semester. So a couple of logistical things. So the talk is being recorded. I would ask that you mute your microphone. And if you do want to ask a question, please either use the chat to write something down or raise your hand, and I'll be monitoring the Zoom raise hands feature and will interrupt Matt when there's a natural pause to give you a chance to ask your question. At the end of the presentation, we'll thank Matt and have a Q&A period, and we'll try to end pretty promptly on time so that if you've got additional questions that you want to pester Matt with, or if you want to just generally socialize, we can all gather in the GatherTown CAM space, and we'll put the link in towards the end of the talk when everybody who is likely to join has joined. With that, I'll hand things over to Matt.
Thank you so much for having me. I think, like many of you, this summer I was somewhere I wasn't expecting to be and thinking about problems I wasn't expecting to be thinking about. And one of them is this modeling COVID in small colleges. And not that particle systems aren't interesting, but I agree the timeliness is different for that. But just to give, and I'll mention the people who are on this, this is an NSF project, those details to follow, but I do want to say something about my background and how this project came about. These pictures right here are from particle systems that I studied in the past. And I think of myself as a pure mathematician. Certainly that's my training, theorems and proofs. And typically though, about interacting particle systems, which is time evolving randomness with interactions occurring. And that general definition includes disease spread and epidemics. And towards the end of my postdoc, which I did with Rick Durrett primarily, I started thinking about epidemics on networks, but from this very theorem proof perspective. And then things started shutting down in March and April, and I wanted to see if I could do something helpful. I think like all of us, we wanted to, or just felt urgent, and like if you could do something that seemed like a nice thing or important thing to do. And I turned my attention from my particle systems and instead thought of a very concrete question to ask, and that is, how does COVID-19 spread through a college? And it's not a coincidence I asked this question. Actually, photographed here is Bard College, one of the more classic architectural parts of Bard College. And that's where I was last year, and that's where I was passing the quarantine. I actually was in the Hudson Valley on campus for basically all of spring and summer. So I had, let's say, familiarity with this setting, and it seemed like, I'll get into this more later, there was a lot of modeling done for medium and large colleges, but not a lot of attention to small colleges. And again, I'll say more about that later. So how to approach that? Well, as I said, I'm a pure mathematician by training, still think of myself as a pure mathematician. So for sure I needed help and different perspectives. And this frame filled my computer basically every day from the start of this project to the end of August. And It's conveniently oriented, I suppose, because the co-PIs, Felicia and Nicole, are in the top of this figure. Felicia is a biologist who specializes in infectious disease, and Nicole is a computer scientist, mainly who thinks about networks. And something unique about so the three of us on the top of this frame, we applied for a rapid grant and it was accepted. And a unique part of that was it included funding for students as well. And below, there's Riti, Kukai, Lily, and Sasha, who are all students at various stages of their education. Lily is here at CAM. And I don't know, I mean, just to pause for a second, it was just from the perspective of working together and solving this problem, it was this very innovative, just enjoyable process. I guess I won't dwell much longer on that, but it was just a very, very good team experience. I had a wonderful experience just from the perspective of tackling this problem that none of us were like particularly, or I don't think anyone is well equipped to deal with this COVID, or just it's all this new territory. And it was a great adventure, I would say. Introduction aside, I don't want to assume much background in modeling. So let me start by talking about just the big picture ideas for how large scale models are working. So these are things on the order of like predicting what happens in a country like the UK or the US. There are three primary paradigms, I suppose, for modeling a large population and how a disease spreads through it. The classic and probably still the most widely used is what's known as a compartment model. And in these models, you take a population, you stratify them into compartments, and then you assume that these people in compartments interact in such a way proportional to their size. So if you're talking about disease spread, usually you think of a certain segment being susceptible, a certain segment being currently infected and spreading the disease, and then some people who have recovered. And the way these compartments interact are specified by differential equations that come from parameters for how quickly disease spreads, how people recover or progress through whatever disease you're modeling. And these, as far as predictions are concerned, these dominated, well, they're still very relevant, but at the early stages of the pandemic, a very famous compartment model came from Neil Ferguson, which was known as, and his team, which I think of as the imperial study. I believe that's what it's called. And this was the very first like eye-opening model that was saying something like 1 million deaths in the United States with no intervention and 500,000 in the UK. And I think this and some other information that came out at the time was a big mover in this, or big influence on policy shifts that we saw in March around the globe. And I will say that these models typically do not use three compartments. Usually the number of compartments is quite large, and you stratify based on demographic information or even location information for your population. And then you get very huge systems of differential equations that you numerically approximate. Another very popular type of model that is, I think, one of the most visible now are curve fitting models. And with these, it's a regression problem. You take data from the past and you use it to build some sort of predictive model to guess what will happen in the future. And so many places are doing this with slightly different flavors. And just as a sign of how popular this is aggregated from 538.com. Many mainstream models or popular models from different organizations. And yeah, one, or notably missing from this is any randomness or notably missing from this is randomness or thinking about the disease dynamics. It's really a data-driven problem or curve-fitting problem. I mentioned that I'm typically studying particle systems, a relatively new paradigm in epidemic modeling. Comes in the form of an agent-based model. And what is pictured right here, probably difficult to recognize, it's Bogota, Colombia. And how agent-based models work are you truly model a space. You make true to scale, or it can vary, but how many agent-based models work is you actually make a spatial setting, you populate it with people, and then you give these people routines that they follow. So each agent in this model has a house they live in, they have a job that they go to, some community they interact with, and you do this on a huge scale. So you put up like, on the scale of millions of agents is possible in some of these models. And each of these people go about their lives, and then a disease is overlaid onto this population that spreads when people get close to each other. And I think modern computing power has really made these possible. There's some clever ways that you can actually work on the scale of 1 million people. And what is sort of neat from a philosophical or maybe mathematical perspective is that relatively simple rules for how people live gives rise to this complex global structure, which makes predictions that you couldn't really make using those other two paradigms I just mentioned. So it's an exciting thing, and it also looks like an interacting particle system to me, so I personally like it. Now, this is not meant to be exhaustive at all, but those are 3 big ideas in disease modeling. And that was just to get us warmed up for talking about a smaller scale question, which is how does disease spread on a college campus? And historically, this is not a commonly studied question to go to a college campus, but with this pandemic, it suddenly has become an extremely pressing question to understand what is going to happen when schools try to reopen, and how will this disease that very few people have immunity to spread in these campuses? And most importantly, what can administrators and students do to make this a tenable situation or a doable situation? And there's really no precedent for this. So if we want to make informed decisions to the best of our ability, we almost have to turn to models to do this. And in addition to that, there really was a short time window. This had to happen basically, I think people realized this in April, that, okay, what are schools going to do? And then we just had 4 months to figure out to the best of our ability what's going to happen and how we can affect these outcomes. So I'll give a quick flyover of a few university models I'm aware of. Something I would really appreciate is, not during the talk, but maybe afterwards, if you could point me towards any other models that you know of, that would be fantastic. Yeah, more on that in a bit, but if you notice I'm missing anything or would like to add anything, please let me know after my talk. Oh, and it's not coincidence that Cornell is pictured, because Cornell has kind of been a big driver for these university models. So it's not just pandering to the audience, like really Cornell has been great for producing this information. One of the first papers that I'm aware of that came from Whedon and Kornfeld. And what they looked at was the induced network from courses at Cornell. I think they actually got a hold of this information from some past year, and they made a network where each node represents a student, and an edge is present between 2 students if they share a class. What question were they interested in studying? They wanted to know the effect of, if you start removing large classes from your offerings, making them online, what does that do to the connectivity of this induced network? So if you say cap classes at 100, does that fragment the network so that a disease couldn't spread through classrooms? And my impression of their findings were that they were a little discouraging, that even getting rid of all large classes did not shatter the network. And in fact, it did very little to even reduce the average distance between 2 people in the network. The exact cap is evading me. I want to say there's 60 or 100 is where they capped it. And after doing that, the average distance between 2 people went from like 2.5 edges to 3 edges. So disease could still spread. And I guess the conclusion was only making classes remote or removing large classes is not enough, was the main takeaway from their work, which, yeah, I don't think anyone thought that would be enough, but this painted a bleak picture for the impact of that alone. Another approach, and this is being done at Cornell by Fraser and his team, is a compartment model approach. And forgive me if I misquote anything, I'll be sort of crude. The Fraser and their team are trying to model how COVID spread on Cornell's campus using very accurate information about biology for the disease, and various compartments for different subsections of or communities in the campus. And their ultimate dynamic, though, is a compartment model, which they're trying to make accurate. And please anyone interrupt me if they feel I'm misrepresenting anything from Fraser's team. But I think something unique, and I've gotten that impression more from talking to some people from here, is how much Cornell administration is relying on this modeling and is listening to these modeling efforts to make policy decisions. I will say that one possible shortcoming of this model is that it is a compartment model, and what compartment models tend to do is they assume that the population is mixed inside of each compartment. And so just unavoidably, you're going to lose some of the structure in your community when you use a compartment model. And on college campuses, it seems like there is a lot of actual structure happening in people's lives. One other compartment model came from Patiel, Zhang, and Walensky. And they used actually a 3-compartment, very simple model on an abstract population of 5,000 people, students, and just a SIR model. And they asked a very concrete question of how frequently should we test the population and what degree of accuracy in our tests is needed. And they approached this from a cost effectiveness perspective. So how do we keep COVID down while minimizing costs? And the recommendation was actually fairly intense. They suggested screening the entire student body of 5,000 every 2 days, but with relatively low specificity. So with 70% test accuracy when you do that. And while they found there are other ways that you could keep it down, that was the most cost effective to have low accuracy, frequent testing. And they found that even weekly screening is not enough, that if an outbreak occurs, it is often uncontrollable. And again, this used a compartment model, so it is smoothing over some of the structure that really is there. There is one agent-based approach that I'm aware of, and this came from Gressman and Peck, who are professors at UPenn and Swarthmore, and they used the University of Pennsylvania as their prototype. And in particular, kind of urban campus, 20,000 or so students. And how do they do an agent-based approach? So this is a figure I made, is not from their paper, but this is my understanding of what they do. So think of each student on the campus as a blue person. So let's think of this blue person as a typical student, and how they model the day-to-day life of each person on campus is they think of how many contacts a person has on a given day. And for whatever reason, they say that on average, a given person will interact with about 20 people each day. And the proximity of these, or intimacy of these interactions, is on a sliding scale. Like there's the person you live with, like a residential contact, there's your close friends, social contacts, and there are people maybe you study with who are academic contacts that are close. And then the distance goes out where maybe it's people you share an elevator with, someone that you stop by incidentally at lunch, or brushed past like on a path connecting two buildings. And they overlay a disease on this by each of these interactions carries some risk of transmission relative to the proximity in space if someone in that interaction is infected. And this is agent-based because they build this routine and they specify who you interact with by giving everyone a course schedule, giving them a cohort, like a year that they're in school, and having them select their contacts from these groups. So people have routines. Notably, to me, this is not necessarily a spatial model, but it is agent-based in the sense that everyone has their own lives and they overlap in these various and somewhat natural ways, and then disease can spread when that occurs. Can I clarify anything about this overview I've said? I'm going to switch to what we chose to tackle at this point.
So there's a question from Steve Lance.
Hi, can you hear?
Yeah, sounds good.
So I was wondering if this agent-based model includes random interactions, like every so often there are just contacts that are not part of a network.
But from random interactions with people on campus, other students,
Well,
or
yeah,
or
the
the
agents
community.
can, there's, as the evolution proceeds, that there's like crossover. That's
Yeah.
random. Yeah.
Yeah, so these broad interactions,
Yeah.
they're just going to pull 4 people at random, say, from the entire population that you bump into.
Good.
If
Thanks.
that, okay.
Yeah.
So, harkening back to the question, we want to know, how does COVID spread on a small college campus? And these models that I mentioned before were for larger communities, and often they weren't fully taking into account the structure of a college. So there are a lot of small colleges in the United States. I think they serve over 1 million students. It seems important to ask, are there key differences? Are there meaningful differences between these smaller colleges where maybe they are better situated to control COVID spread, or maybe they're worse, maybe they're breeding grounds for disease spread? And can we say something about that mathematically? This was in the cards from the start. We are going to take an agent-based spatial approach to modeling this question. And in particular, we're going to make a network that represents a physical campus. We put students and faculty on this network, and then we give them routines where they move from place to place throughout the day. And on top of this, there's disease spread. So unlike the models I mentioned before, our network is actually going to represent a physical space, and agents are going to be particles on this space that move throughout it and interact. The advantage of this is, because it's spatial, we can make it fairly high detail to, especially when we're talking about a small college, we can make it high detail to what a small college will look like. And from a broader perspective, because it's agent-based and we're giving people routines, we can focus more on making how people move and interact realistic, and count on this self-organizing on a larger scale to maybe give us interesting insights about the big picture for disease spread. I'll spend 5 slides or so giving some details about what we exactly do, but the main takeaway is that we're going to make a network that represents a college, put people on it, give them realistic lives, and then have disease spread take place on top of that. Step 1 is making a network, and phase 1 of step 1 is designing the building blocks of the network. So we needed a way to represent buildings as a graph, and what we settled on was to use a star graph to represent each building. This figure right here, let's say that this is a building that houses classrooms. So the core of this star graph is going to be kind of collapsing all of the common space of that building into one vertex. So the core of this star represents the entryway, the hallways, the elevators, the bathrooms in that building. And then the leaves of this star, those are individual classrooms in this case, or they might represent sections of a dining hall or sections of a library. So how we represent buildings in our network are star graphs, where the core is all the common space. The leaves of that star are either specific rooms or sections of that building. And with those, we can put them together and make a campus. And our inspiration for our campus design came primarily from Bard College, because that's where many of us were, and we had students who attended that college and professors there, and we could look up information, which is kind of just the easiest to get a grip on how to design ours. And so this is a campus that has about 2,000 students, and only small classes. That's another distinctive feature of a small college, is the large classes are just not a thing. So I think the largest class we have has 20 people in it, and that counts as a large college in a liberal arts college setting, or a small class, or a large class in a liberal arts college setting. Hopefully much of this is self-explanatory. Academic buildings house classrooms, dorms house students who are living on campus. There's a gym, a library, a dining hall, faculty offices. One space that I do want to call special attention to is the social space star that's in the top left of this schematic. And a challenging question and really just feature of college life and let's just say college life is how do you incorporate socializing into a model? And keeping with our star graph paradigm, we decided to represent socializing as a building. It really just represents an abstract space, and each of these leaves represents a clique of friends who spend time together. And so the socializing actually is represented as a star graph in our network, and we make it such that the number of leaves are that there are about, on average, 20 people in each group of friends. And then throughout the day, these friends will inhabit that space and interact with some subset of them. So yeah, I'm not sure how clear that is coming in cold on this model. If I can clarify anything about that as I go, please stop me. And because this will be an important feature of our model, but just to say that one more time, the social space doesn't really represent a like physical building or space on campus, but just when an agent goes there, that means that they are spending time socializing with whoever else happens to be at that space at the same time. And we segment that into smaller cliques of friends.
Could I ask, please, Matt, that social group, are those social groups persistent over time, or are they randomly constructed along the lines of a well-mixing assumption?
The social groups are assigned at the onset of the model, like who are the 20 or so people that you interact with. And yeah, so it does not evolve over time. It's fixed at the beginning.
Great, thank you. Yep.
Super. Just because we have it, this is the actual network that we used. So like I said, we're going to have particles move throughout this network pictured right here, true to form of what we use. There's nothing really I can say more about it, but that's it. It's kind of a nice image. As for the agents who are populating this network, we have on and off campus students, so students who reside in those dorms or students who reside off campus, and 400 faculty is how many faculty we needed in order to teach every class when we assign people to classes. As for disease progression, certainly more detail could be given, or more detailed disease modeling could be done, but how we picture someone progressing through the stages of COVID is that initially everyone is susceptible, they could get infected. If someone becomes infected, they're in an exposed state for some period of time, upon which they transition to being infected, but asymptomatic, so they can spread it, but they don't have symptoms quite yet. After which, three things can happen. They either develop mild symptoms, develop extreme symptoms, or they are asymptomatic until they recover. They never develop any symptoms. And we have different amounts of time and infectiousness attached to each of these states and transition periods. Okay, so we have the people, we have the network, we have to say how they move through the network next. This is kind of an eyeful, this slide, but what this is describing, or what is an example of, is how we break up the schedule for each person in this model. So noteworthy about this is we break the day into hour time slots, 14-hour time slots starting at 8 and ending at 10. And at each hour, everyone has a place to be. So if we just look at, say, this far left column, only look at this far left column for an on-campus student on an A day, we think of days as alternating between, say, like your Monday, Wednesday schedule and your Tuesday, Thursday schedule. But this student, for example, on Monday, they start in their dorm room, then they go to the dining hall, then they go to their first class, and so on for those different spaces you saw in the network. So we have some algorithm that assigns everyone a class schedule and then places that they go throughout the day. And for each building that they choose to go to, actually I should probably show how that happens. So everyone has this schedule. Hopefully that is somewhat clear what we're doing with that. And then just to go back to our schematic, how motion happens is, imagine that a student wakes up in their dorm room and that they intend to go to their first classroom. how motion happens on our network is at the end of the hour, the student, who hopefully you can see this hand in the top right for the dorm, they will go to the core of whatever building they're in. They're in the common space now. And then they will go to this central vertex, which in our representation represents all connective space on campus. So this is a huge reduction, but we collapse all of the outdoor space, all of the connective hallways, everything to get from A to B into one vertex that everyone goes through at the end of each hour. So in any case, the student woke up, goes to the center of their core, goes to this common space. They want to go to their classroom. So then they go to whatever classroom building they have to go to, and then to that classroom. And at each stage of that traversal that they do, there are other agents who are possibly in that same space, and that's when infection can occur. And that would be the last thing I want to say about how we model or how we built this campus up. Or can I clarify anything else about how we are giving people routines and how they're moving through the network? So at this point, this is a functioning college, or this is how our college is working. It looks like 2 questions. Go ahead.
Alex.
So in creating those schedules, did you make them conform to a common schedule of students in that specific college? How did you decide whether or not this is typical? What is the spread of different schedule types among your agents?
Sure. So there's some easy common choices to make of like they start and end each day in their dorm. We gave everyone 4 classes, which is a bit of a simplification. And we have them try to go to the dining hall 2 or 3 times each day in like normal time slots. And after that, they only have maybe 4 or 5 hours that are unaccounted for. And we tried to allocate their time in a somewhat sensible way between spending that time socializing at the library, at the gym, or just back in their dorm room. So whether
and
it's... Please.
The fact that similar people in the same major are more likely to end up in the same classroom than others, where is it represented here? How do classes
we give everyone a division, so we have a smaller population, so people are either STEM, humanities, or arts, so there's sort of 3 designations, and they are taking classes. I believe 2 of their classes are only in their division, and then 2 are just randomly throughout the population. So there's some correlation between people who are in a like category as others.
I see. Thank you.
Sure.
Alice?
Do the students change their behavior when they have symptoms? Like, will they skip class when they have mild symptoms?
That's coming when we do interventions. In our unintervened campus, students are just going to show up to class even if they're sick. So yeah, I'll get into that once I start having COVID happen, or we start having COVID happen.
Okay.
And which we're almost ready to do. So now imagine the last thing I have to define is how does disease spread happen in this. Hopefully you can picture people moving through the network and co-inhabiting spaces. How disease spread happens is if a person is susceptible and they co-inhabit a vertex as they're moving through campus with some number of infected people, they will, with some probability, become infected at that time. And we scale that probability proportional to the number of people infected divided by the size of whatever space they're at currently. And we include a risk multiplier for if they're in a riskier setting or less risky. So we make it sometimes 2 or 3 times more likely for an infection to spread in a given space. And hopefully that's clear, but like so for instance, if there's 16 people in this room and 2 infected, each of these gray people will with some probability become infected at this point in time, each independently with the same probability. And with that, we now have something, assuming that we chose good parameters for infection or for the stages of COVID progression and for our space and everything. We now have a campus on which COVID or a disease is spreading. And the first question to ask is, what happens if we do nothing? If we, if like I said, students are getting sick, but they're still showing up to class. This is kind of some bizarre reality where like 60% of the campus is infected, but you're still going to class and acting normal. But in any case, this is our comparison point in our base case. So in this scenario, at least we make a choice so that the average R naught, the average number of people each person infects, we have that around 4 in this picture right here, and then we assume no intervention. And this is more just to make sure that our dynamics are working and everything is compatible with that. We see about 80% of the campus are infected after 100 days. And peak infections occur about halfway in. So I'll refer to this as our base model, and this is going to be our comparison point to see how, obviously no one is trying to do nothing and then open campuses. And the question is, what interventions are most effective and what combinations should colleges be considering using? And the starting point to investigate intervention effectiveness is to take this base model that I just showed you and overlay only one intervention. So what we have here is, imagine a college in which everything is normal except students are choosing to socialize less, spend less time socializing together. Is this first column or second column? Or imagine a campus where it brings back half as many students, but then everything else is as usual. And also face mask use happening, and then testing and quarantine is this last category that we considered. And what we see from this is that testing and quarantine and face masks appear to be the two most effective interventions just by themselves. Although fewer students looks comparable, it's a bit misleading because there are half as many people on campus to get sick for that particular intervention. And in this panel B, so again, where is this coming from? I guess I should say that also. So we have this model, and so now we can actually just simulate. I think we simulate 40 semesters and we average over what happens on those 40 semesters when we start with initially 10 people infected. So we imagine there is an initial outbreak and we ask, does that grow, or how much does that grow on a campus of various intervention? Peter?
Yeah, I'm just curious. So for the testing intervention, this isn't testing and then they go about their daily business. There's something happening as a result of the testing, or what exactly is changing when they're tested?
Yeah, I'm happy to elaborate on any of these interventions. So with testing, we assume that anyone who has symptoms will go and get tested, or basically they wait a random amount of time and then they get tested, but people who are symptomatic get tested, and upon a positive test, they are removed from the population. They quarantine for 14 days immediately. Well, and then we also assume that screening tests are performed on the whole population to catch these asymptomatic cases or pre-symptomatic cases. And in this particular panel, we're assuming weekly testing of the whole student body with a 2-day turnaround for test results.
Okay, and is testing the only situation where quarantine is implemented?
Yeah, so something noteworthy missing from our model is we do not have contact tracing. So we don't quarantine people who are in contact with others.
Thanks.
Mm-hmm. Was there another question?
Yeah, Alex?
Do you assume the testing are perfectly correct or they have mistakes?
We have mistakes consistent with what some of the others were using. So I think the false positive rate is 3 in 1,000, I think, and false negative, I'm not remembering exactly our false negative rate. Lily can chime in if she remembers.
Maybe 1%. Is it?
Maybe 1% sounds what the number in my head also. Yeah, thank you. And just because it was not a challenge to include, in this panel B, we decrease the amount of time until tests are returned and see the expected effect that there are less total infections if you have faster turnaround for test results. Steve?
On your parameters, you mentioned that Peter Frazier et al., they combed literature and got, values. Did you do the same? And I was especially wondering about the risk parameter for different spaces. It seems like there could be sensitivity there, like the risk of the common everybody's there space would be probably very low because it's outdoors. And how did you decide what that low value should be?
We thought these things are were quite subjective, how we made these choices. And it is sensitive to some of these. So it is a little scary putting this out there for that reason. To answer your specific question about that central vertex, we chose our parameters to thinking about the average number of infections that occur over a given week in that space. And we tuned that. So we thought about how many people are there, and we tuned the risk of that space, or actually the size of the space is what we chose to tune, to keep those, or like for instance, in that central vertex, we only have one infection occurring every couple weeks during transit. There's one intervention that I did not include on this, and it's one of our more surprising findings that seems compatible with something that Frazier and his team are finding. And that is that sometimes it is best to keep students on campus where their behavior can be guided, let's say, than letting them off to their own devices. And for sure, an intervention that is happening on colleges are opened now. An intervention that's occurring are building closures. And what is pictured right here on the far left are the number of infections by building type in that base model where about 2,000 people get infected. And then the two columns to the right are how many infections occur if we close the gym, library, and dining hall. And closing a building doesn't just mean that time vanishes where students would have been there, like they have to spend that time doing something else. And we considered two different scenarios. One is an austere closure. And in an austere closure, a student in our model, when they would normally be at the library, they instead choose to spend that time in their dorm room. And that applies everywhere. So anytime there's a building closure, students would spend that time alone in their dorm and being quite responsible. Whereas in reality, it seems quite possible that students will spend some of this unstructured time socializing. And in a social closure, what we have happen is half the time that a student has to spend their time somewhere else, they choose to socialize. And if you make that change, we see a giant spike in infections all across the board. I'll say more about conclusions from that, but hopefully it's clear what is happening, at least in our model, and what, if I can clarify anything about that, let me know. So I have about 5 minutes left, and just a few more things to say. So I think this is probably something that happens all the time when you're doing applied work, but we ran into the situation of relatively few interventions. There's these 5 or so interventions with different intensities, but we realized after we implemented all this stuff that there are over 100,000 things that we could test on this campus, like different degrees of intervention, different behaviors. And the question is, I mean, first off, runtime is an issue. No one wants to see thousands of different simulations. Like, what's an intelligent way to organize or design these interventions to actually give meaningful conclusions? To that end, we separated our interventions into 2 categories. We thought of interventions that administrators can control either before or during the school year, and then behaviors that students can bring to these intervened campuses. So for example, like how often students are wearing face masks, if they're showing up for their screening tests, and how they behave with socializing. Like, do they socialize less? And if a building is closed, are they socializing or spending that time alone? And administrators, they can control testing amount, turnaround time, what buildings are open, and how many students they actually bring back to the campus. So we separated each of these things, policy and adherence, into 3 levels of intensity. And now we go from 100,000 to 9 different intervention strategies. And these come from varying the intensity of your administrative policy, and your student adherence. And what this figure shows in the center of each box is the average total number of infections from over the course of a semester. And again, this is with 10 people initially infected. And this figure illustrates one of the bigger takeaways from our modeling, which is that it seems like student behavior is really a major variable in whether a campus can open safely or not. So even with, I'm happy to go into detail about what we define low, medium, and high policy as, but even in fairly intense policy settings, if students are not also doing their part, it doesn't seem like it's safe to reopen. So we are recommending that students take this seriously and realize that they are a key player in getting to be on a college campus. Can I clarify anything about this figure? Peter?
So is this all policies at a high, low, or medium setting, or is this a sort of certain ones? And if so, if it's all of them, have you broken it apart to look at what different policies play the biggest roles?
We're
student
assuming
behaviors?
so we're assuming that those marginals where we just put one intervention in give some information about what is more important to focus on. And these combinations these tables, they're not really intelligible to look at these tables and get much from them, but when we define a high administrative policy, it sets the amount of screening, turnaround, and how many people come back and what buildings are open. And we don't play with those once we set that. So hopefully that addresses your question.
Yes, thanks.
Super. And let's see, I was told I was giving this talk at a liberal arts college actually earlier this week, and I was told by one of the professors there that another liberal arts college, Haverford, their opening plan is just heavily relying on student behavior. They're claiming that Haverford students are devoted and we can safely reopen because of the students, and they will comply. So they're actually gambling on this effect that we're seeing here, that like it's in students' hands and they believe in their students. And yeah, maybe it's true that liberal arts colleges inspire more devotion and more of a sense of belonging to a common cause than these larger campuses. I can't really speak to that being true or false, but possible. I mentioned key takeaways. Key takeaways for administrators, we think, are to shoot for thinning the total campus population by a half, bring back half as many people, at least weekly testing of every student, and consider keeping buildings open to impose more structure. These are spaces that you can actually monitor how they're used, and you can keep social distancing and good practices. You can enforce those things. As for students, we see that it's important to wear face masks when socializing in small groups, and in general to socialize less. And it seems like an obvious thing, but apparently there have been issues with this, showing up for mandatory screening tests. Thank you for your attention.
I'll unmute all of us, or I suggest we all unmute, and I see a number of people applauding. And we have about 10 minutes for Q&A, and then we'll go to the GatherTown space that Erica just posted in the chat. Questions?
Okay, well, maybe I'll jump in there if that's okay, David.
Of course.
So if I'm supposed to raise my hand or something, but yeah. So Matt and I talked earlier today about a number of these areas. So I guess I have a couple of questions within the model, please, Matt. Your model of infection within each space where you look at the density of people, essentially. Have you thought about maybe nonlinear functions of those ratios in places? I can imagine situations where students would cluster within a large area, and then other situations where they would not. And so I'm curious if you've thought about doing versions.
Not until just now, but that does sound like a nice idea.
Yeah, I think it has the difficulty that it's complex and makes the model more complex, not so much from a computational perspective, but more from a interpreting and understanding what's going on. But I can see you've captured a lot of the really nice elements. And then one other question, if I may sneak it in, please. One thing that we had in our original modeling with Peter Frazier is a constant infectivity of people over the time when they're in an infectious state.
Mm-hmm.
And then we've done a bit of reading, and we're learning more and more about how this infectivity peaks around the time that your symptoms appear. Have you thought about that, and is that something that can be incorporated into your modeling?
We did think about that. It currently is not incorporated. We have a constant infectivity. It varies by the degree of your symptoms, but not in a very fine way. So I think we do plan to write a follow-up for spring semester, and that will be having a random or some sort of tail on your infectivity will be incorporated, we think, or hope to.
Wonderful. Thank you.
Thank you for your question.
Steve.
Matthew, one of the most controversial things about the Cornell modeling was the baseline R naught, which has sort of an enormous effect on everything.
Sure.
Right, and you mentioned that yours was 4, right? Ours was 2.5.
Yeah, ours was significantly higher. Yeah.
Or can you comment on why you did that?
There are 2 reasons why. So for whatever reason in our model dynamics, if it is 2.5, even with no intervention, there is not a large epidemic. So it's like a constraint of our model. So we want to actually have an epidemic happening and see how things bring it down. And it also does not seem too far-fetched to believe that R naught is higher in a closed community like a college setting or liberal arts college compared to just broad community spread. One
Okay.
second. Just 1 second, please. I think everyone's had that happen at some point.
Absolutely.
Yeah. Any other questions?
Alex.
Hi, thank you for the talk. I'm teaching a math modeling course right now for undergraduates. And one of the biggest issues which I struggle there every time I teach it is communicating effectively the distinction between the qualitative models, which are meant to showcase different mechanisms which might perhaps cause phenomena you're interested in, contrasting those qualitative models against the quantitative ones, which are meant to give accurate predictions and actionable recommendations. And the modeling principles, some of the modeling principles for those 2 classes are quite different. Mm-hmm. With such a high number of parameters, which usually go into constructing an agent-based model, are you nervous about the recommendations which you are giving to the administration? Because you are giving very quantitative recommendations about 50% reduction, for example, etc. Mm-hmm. What kind of validity testing and sensitivity to parameter change have you performed in this model?
To answer your first question, yes, I am nervous about making recommendations about these things. And it's a spot on comment that we are taking a qualitative model where there are, dozens of parameters, and many of these are actually, it's quite sensitive, the choices for these. So a lot of these choices will displace infections and move them to other places when we have R naught fixed. But we for sure have, there is a lot of sensitivity in our model, and it is scary to be making such concrete recommendations. But at the same time, it is the best we can do. And so we are willing to put it out there for that reason, because there just is, it seems, yeah, nerve-wracking, but ultimately justified.
Matt, may I add something to your comment, please?
Please, yeah.
Yeah, I agree. I think it is nerve-wracking. At the same time, the administrators have to make decisions, and they do want to know something about the relative impact of the different measures one can impose. So I would say, even though we're modeling with exponential growth, which is always a dangerous thing, better a sort of a careful modeling approach, facing the fact that there are uncertainties, than not modeling at all.
There's a question from Frank still.
Thanks. Very nice, clear explanation. Thank you very much. One of the issues specific to Ithaca and Cornell is it's a college town with a population outside the campus. And in particular, there are concerns amongst the external community that interactions, say, at bars or grocery shopping or the like, are going to be an issue for the outside population rather than the student and campus population. Yeah. I can see sort of how you could allow for that by expanding the scope of your model tremendously, but have you any other general comments on that?
I'm thinking about the interaction with community that's happening at these more isolated places. Is that correct?
Yeah, more or less. Somewhere along those veins, yes.
Our perspective is we're really asking what happens inside of the college. We're not asking about the impact the other way. So the main interest from our perspective is how much infection is coming in, not how much is going out from it. So we didn't take that into account, and that feels like a very community specific type of question. So like asking about Ithaca seems really reasonable, but every college is situated somewhat differently in their community. So we didn't attempt to address that.
And maybe we'll let Steve have the last question as we're getting pretty close to time.
Yeah, I just wondered, what do you think that you learned from the agent-based model that was not so apparent, say, from a compartment-based model?
I hadn't thought about that. Let me think for just a moment. Well, I think it comes back to just the starting point for an agent-based model is the way the interactions are happening is much more natural. It feels more like a campus when we're actually implementing, or when this is running. And what's the extra thing we learn from that? Hopefully socializing and just normal our interactions are, as I said, more natural. And I'm not sure how that reflects in our takeaways. Can you?
Yeah, I totally buy that. I mean, no problem accepting the premise that having something that feels more like a campus is really interesting. I just wondered if there was something that's surprising that came out of that that was diverging from what might be in a more generic.
Yeah, that you could infer from these more generic type models.
Or maybe you could say that the conclusions were entirely consistent with compartment models, and that would also be, kind of an interesting conclusion to make.
Lily has her hand up. I don't know if that's to volunteer information or another question.
Can I comment on something?
Go ahead.
Please.
I think one thing that came up in our modeling was that I think is somewhat specific to an agent-based model was when we're tuning some of the parameters. because these parameters are very sensitive. A lot of these parameters are very sensitive to like perturbation, and like just changing it by a small fraction can change, you know, the network reasonably by like shifting some infections elsewhere and stuff like that. What we found was tuning the capacity of social spaces, or like how much people you interact in the social spaces, things like this. Having like less mixing will actually change infection somewhat drastically. And I feel like to have an agent-based model, it just, by looking at the effect of these parameters, it justifies the model slightly more. And it's, in my, like, I feel more safe about like making certain assumptions because we see the actual effect of certain parameter changes. If that makes any sense.
Yeah, and you, building on what Lily said, is like, because it's spatial, you can see like when you make these choices, are reasonable things happening in the model? Like, are people piling up in one space? Or are you getting like absurd numbers of infections in a given area? So I should be able to speak better to if it's different, our insights that our conclusions we're drawing. I can't speak to that, but we think we're happy that we put this different approach out there, and we hope that it gets built upon more.
Yeah, you do get more insight into different aspects of dynamics, I think, this way.
And on that interesting note, I suggest we thank Matt again, and we can bother him with more questions in the reception afterwards in the cam space, which is again in the chat. Thanks, everybody.
Thanks, everyone. Thank you.